I am Nikita Lipsky, and today we will talk about JIT versus AOT. What a boring slide. That slide is much better. So meet for JIT team is Freddy Krueger, and for AOT team is Jason Voorhees from Friday 13. You know, all compilers are monsters. So every epic story should begin with once upon a time, when C++ was cool and new, all compilers were static. C++ was compiled statically, Fortran was compiled statically, and even Pascal was compiled statically. Until into this world came Java. No, Java didn't invent dynamic compilation, but thanks to Java, dynamic compilation became a mainstream. So if we talk about Java, we implicitly mean a JVM and a Java bytecode that is executed on that JVM. And JVM can execute bytecode by two ways. It can interpret it, that is slow, or it can compile it down to machine code that will run directly on the underlying hardware. But there are also two moments in time when such compilation to native code can occur. Dynamic or just-in-time compilation occurs at application runtime, while static or ahead-of-time compilation occurs before program execution. Let's refer to the next slide. Here, above the dotted lines, you can see what happens before program execution. Underneath of the dotted lines, what happens at application runtime. On the left, you can see conventional JVM, such as the Oracle HotSpot. What happens there? Your source files are translated into class files that are then put into jar files. And at runtime, classes from jar files are loaded by the JVM, and they're firstly interpreted by interpreter, and with the help of profiler, it is detected hot code that is fed to JIT compiler that produce native code that runs directly on underlying hardware. In the middle, you can see JVM with the ahead-of-time compiler. As you can see, all your class files are translated into machine code, into native executable, before program execution. So your application starts on the underlying hardware right from the start. In more general case, however, some classes can be unknown before application execution, such as third-party plugins and dynamic proxies. So even a JVM with a ahead-of-time compiler should be equipped with a just-in-time compiler or interpreter. What we are going to talk today. First, I would like to dispel common myths around Java ahead-of-time compilation. Then I will show you what challenges it actually has. And then we will talk about all dispute, what is better for performance, dynamic or static compilation. And finally, we will talk about application of dynamic and static compilation in various fields of use of Java. Client-side, server-side, embedded, IoT, and mobile. But first, let me introduce myself. For nearly 2 decades, I have been working on Excelsior JET project. It is a complete JVM with a ahead-of-time compiler certified as Java compatible. And I have been working on this project. I worked on this project from the day one and contributed to all its components. On this slide, you can see a Java compatible sign. Actually, we sweated blood to get the sign. Some microsystems before and Oracle now do not give this sign to everybody. This sign in particular means that our implementation is Java compatible implementations. And thus, static compilation is possible in full conformance with Java SE specification. And the next slide proves that it can be useful. It is our customers, only a few of them. Since inception of Java, numerous myths have been developed around Java static compilation. And I would like to start my presentation with dispelling those myths. And first myth is Java is too dynamic. It has the following features like reflection, dynamic class loading that make Java static compilation impossible by its nature. But let's look closer at those features. What is essentially is reflection? It is some metadata about your program. Class names, field names, method names. Nothing prevents static compiler to just put that data into data section of resulting executable to let runtime routines to use it to enable the reflection. In other words, reflection just works for statically compiled code. As to dynamic class loading, yes, a completely new class can appear at program execution. It can be downloaded from internet or generated by a framework. But I would like to point your attention to the fact that 99.9% of your classes are usually known before program execution. So nothing prevents you from compiling those 99.9% of classes statically and let remaining 1/10% of classes to be handled by dynamic compiler. So the dynamic class loading does not prevent you from compiling absolute majority of your application classes statically. The next myth is AOT kills the main Java principle. Vora, write once, run anywhere. But listen, this principle sounds like write once. It doesn't sound like build once. It means you can compile your application, or you can write your application once, build it for every target platform, and run it anywhere. Moreover, many desktop vendors already distribute their applications in platform-specific installer packages. And for those vendors, adding a static compiler is just an additional step in their build process. And if you're on the server side and use Docker, for instance, please note that Docker image is platform-specific as well. And the next myth is, if Java had a static compiler, it would transform into sort of C++. That is, if I have a 100 kilobyte jar file, I can transform into 100 kilobyte executable that I then can send to my friend that will execute it without having to install any Java. Okay, but Java comes with thousands of standard classes that any Java application can use. How they will appear on my friend's PC? And what about garbage collector, reflection? What I would like to say, both C and Java have runtimes. But C runtime is very small. It can only allocate and deallocate memory manually. And its standard library is also small, like stdlib, stdu. Java standard library is way bigger, and its runtime is much more sophisticated. But anyway, using a static compiler, you can compile your application classes along with standard classes and needed runtime support into one executable, but that executable won't be small. But it can be smaller than the whole Java runtime because static compiler can compile not all platform classes, but only those that are actually needed by your application. It can help to reduce installer packages in a great extent. Previously, I have been trying to convince you that Java dynamic class loading does not constitute any problems to Java static compilers. If I succeeded, congratulations. I have cheated on you. Actually, there is one feature in Java that causes a big headache to Java static compiler writers, and I'm talking about custom class loaders. In your application, you can create at any moment a custom class loader that will override standard class loader logic, and then class reference resolution in your application will function as you define. Why custom class loaders are used today? They are used in Java EE, where multiple web applications can be deployed into one web server, and to isolate them, they are loaded by separate class loaders. And they are used in dependency management frameworks like OSGI. And with all those modern frameworks, there are entire clusters of Java applications that have their majority of its classes known before execution, but unfortunately, all those classes are loaded by some custom class loaders. So how can we compile such applications statically? A compiler has no way to know how to resolve references in such applications between classes. And first, it can give up to resolve references and compile each class in isolation from others. It would work, but won't good performance because to make your application to perform fast, a compiler should resolve reference to enable inline substitution between classes. Fortunately, there is another solution, albeit partial. Actually, developers do not write their own class loaders. By the way, how many of you have ever written your own class loader? Okay, but usually developers don't write. They use ready-made frameworks that employ custom class loading logic internally. Thus, we can learn how class loaders work in those most popular frameworks and support them at the JVM level if they were standard class loaders. And I'm going to demonstrate you how to do that. Let's say we have an application that has majority of its classes known before execution. But unfortunately, all those classes are loaded by some custom class loaders. And first, the compiler should know how many and what type of class loaders will be created at runtime. How it can be done? By inspecting the structure of application. For instance, if we are dealing with Eclipse RCP, where each OSGI bundle is loaded by some custom class loader, we can scan plugins folder to know how many class loaders will be created at runtime. And then we should name those class loaders. It is known that several classes with the same fully qualified name can be loaded into one JVM, provided that they're all loaded by separate class loaders. And in order to differentiate such classes, we need to add prefix to each class name with its static class loader identifier. So how can we name class loaders? For instance, if we deal with Eclipse RCP, where we can choose a plugin name for class loader unique identifier, which is unique in Eclipse RCP. And after we named class loaders, we should distribute application classes among the class loaders. And after that, we can resolve references both within each class loader and across class loader boundaries. But as you can imagine, compiling is just a half of the battle. We also need to load such classes at runtime. How can we do that? Let's imagine that at a certain moment, a certain class loader wants to load a certain class with a certain name. Sooner or later, it will inform about its desire the JVM, because class loaders cannot load classes themselves. They can only look up classes, delegate class loader requests to other class loaders, and ask the JVM to load a class it has just found. And at that moment, drawing on our knowledge how particular class loader works, we should derive that static unique identifier of class loader from its runtime instance. How can we do that? For instance, if we deal with Eclipse RCP again, we can find that where we named our class loaders by plugin names, we can find a plugin name in an instance field of a class loader instance. And then, if we have class loader name, class name, we can find that class in the executable and load it. But please note that loading of classes, of statically compiled classes, differs from loading them in a conventional JVM. All that we have to do is to create Java-Lang class instance and fill it with the reflection information. All class reference resolutions, verification were performed ahead of time, and code will be loaded by operating system. Talking about practical application of this theory, there is a support for Eclipse RCP and Tomcat class loaders in Excel Servjet. So yes, you can compile your Tomcat web application with all your frameworks such as Hibernate, Spring into executable, and it will work. And yes, you can compile Eclipse IDE statically. So we can claim that for any Java application that has a majority of its application classes and respective class loaders known before execution, we can build a static compiler that would effectively transform into native static executable. So is static compilation of Java applications possible? Yes, for sure. So ahead of time compilation of Java applications possible. But why do you need it? How it can be useful? Let's start from the obvious things. It is known that Java bytecode can be easily reverse engineered with the help of decompilers. Decompilers are free, easy to use, and produce amazingly readable source code, almost the same as original. And if you do not want to distribute your application in almost source form code, you would use a tool that would hinder reverse engineering process. And to-go solution for this problem is obfuscation, and its simplest form, name obfuscation. Name obfuscator replaces all class, field, method names with nonsense, so resulting decompiler output much harder to read. But name obfuscation has one big drawback. If your application uses reflection, or framework that you use uses reflection, you should supply an exclude list to your obfuscator, telling it to not change names that are accessed via reflection. It is a time-consuming task prone to errors. Moreover, what you would like to do with your application in the future? The most probably you will refactor it, renaming class, field, method names, and then you should renew your exclude list. If you forget to do that, everything can work on your development PC, but when you deploy it to end customers, everything can stop working at the most inappropriate moment, and you will even notice it at first sight. So why static compilation is better? First, there are a number of tools that can translate native code back to Java source code. All that you can do with machine code is to disassemble it. But to read and understand disassembly requires from you much more qualifications than to read and understand Java source code produced by decompilers. Moreover, it is much harder to understand what the code does if there is no symbolic information attached to it. And after all that, optimizing transformations that can be applied to a code such as inline, specialization, resulting native code can only remotely resemble the original. Simply put, static compilers protect your code from reverse engineering into the same degree as it were written in C++ in the first place. Next comes the opinion that statically compiled applications should start, Java applications should start faster than on conventional JVM because there is no warm-up cycle involving profiling, interpretation, profiling, dynamic compilation. Is that true? Please, you probably noticed that big applications starts much slower for the first time than they start for the second time. It is true for any application, whether they've written in C, C++, or Java. It so happens because when you start your application for the first time, a lot of code and data should be loaded from the hard drive. On a restart, many of that code is already in disk caches, and your application starts much faster as a result. So what can AOT compiler can help us reducing startup time? Please note that native code actually thicker than Java bytecode due to its low-level nature. For instance, fetching an array element in Java bytecode is one instruction, while expressing the same instruction in native code will produce multiple instructions. So resulting native executable can be significantly bigger than the original jar file. Now recall that the most of the time during startup is spent in loading code and data from the disk. So everything that we won, eliminating the warm-up cycle, we lose because we need to load more code and data from the hard drive. And when we did our static compiler for the first time, it was a real surprise for us that startup improvements were not so significant. But we solved that problem. We do execution startup profiling, which is easy to automate. And during that profiling, we identify code that gets executed on startup. And then we place that startup segment into the beginning of the executable and preload it with sequential reading, which is much faster than random reading on a rotating media. And as a result, Java applications start really fast. For instance, here we compare startup times of 3 applications with similar functionality. All they are RSS readers. First 2 are Windows native applications written in DLL and C++. And third one is Java application. And third group of bars represent startup time of Java application running conventional JVM, and fourth group of bars represent startup time of the same Java application running on a statically compiled. And as you can see, statically compiled Java application runs as fast, almost as fast as their native analogs, while the same Java application running on conventional JVM starts 2-3 times longer. So for this app, Java static compilation class clearly helped to reduce startup time. Next, let us consider performance. Actually, there are two opposite myths regarding performance in JIT versus AOT battle. And first myth is, if we, by compiling Java statically, we are making it equivalent to C. C is faster than Java, therefore, statically compiled Java is faster. So what is incorrect in the statement? Your guesses? Okay, yes, everything is incorrect in the statement. Actually, Java, unlike to C, C++, is managed language. What does it mean in practice? That when you dereference a null pointer or violate a bounds range, you will get null pointer exception or index out of bounds exception that you can catch. In C, you will get immediately a sigfold that you without any opportunity to recover. But this or that safety features of Java do not come for free. And they are not free both for static and dynamic compilers. But the statement that C is faster than Java is also incorrect. For instance, if you write your application in C, you will likely use some native libraries, and not all C compilers can use that native code to optimize your application. On the other hand, all library code is available both for dynamic and static compilers. So even even code from standard classes can be inlined into your application code, giving your application a significant performance boost. But there is also an opposite myth. Effective optimization of Java applications is only possible in the presence of its dynamic execution profile. This myth is the most difficult to bust because the best JVM engineers have been hammering this myth to Java developers' heads for years. But I would like to bust it anyway. So if we talk about performance, we talk about code optimizations. It is not enough to just translate your application to native code. To make your application perform fast, and numerous optimizing transformations should be applied to your code. On this slide, you can see only a few of such optimizing transformations. Please don't read this slide. Discussing all this optimization is far beyond the scope of this presentation. But I will tell you very briefly about optimizations that are especially critical for Java. So what we have in Java? It is common in Java to write programs in very good object-oriented style. We're using various design patterns, frameworks, best practices. So from a place where you need some functionality to a place where that functionality is actually implemented, the control is passed through a long chain of intermediate calls. So a good optimizing compiler should see that chain and inline it all to the caller method. But unfortunately, all calls in Java are virtual by default. So methods called Devirtualization becomes a very important optimization in Java because it's precondition for subsequent inline substitution. And method called Devirtualization can be based on the following three techniques: class hierarchy analysis, type inference analysis, and profile-guided optimizations. Let's consider them. The idea of class hierarchy analysis, or CHA, is very simple. We traverse class hierarchy, taking note of the methods that are not overridden. And if it's so, we can devirtualize such methods and call them directly. And dynamic compilers can even inline such methods unconditionally. in static compilers, but there is one drawback with this optimization. When a new class is loaded, that overrides such a method, it immediately invalidates all its inline substitutions. So dynamic compiler should throw away all affected code, de-optimize it, recompile, and so on. In static compilers, we can't do that. Instead, we insert a check that checks if a receiver object was the subject of CHA. If the check passes, we execute inline body of method foo, else we just call that method virtually. Please note that this check can be implemented quite efficiently with just one CPU instruction. But anyway, CHA has disadvantages both for dynamic and static compilers. Fortunately, there is another technique that often allows us to devirtualize calls always, unconditionally. It is based on the fact that for newly created objects, all calls can be done directly, regardless if some classes of class A exist that override method foo, or will be loaded later. Is it clear that for this code pattern we can call method directly? We know exactly statically know the exact class of that call, so we know the target method. So the idea of type inference analysis is to calculate instances of what classes are assigned to local variable A. And if it appears that all possible sources of such assignments is new operators on known set of classes, and method foo is the same in all those classes, we can call method directly again and optionally inline it. But code pattern where we assign new operators to a local variable is not very often. Moreover, we have some other calls that are assigned, the result of them are assigned to a local variable A. So how can we devirtualize call in that case? Let's suppose that we know that method bar always returns instances of class B, and method bus only returns instances of class C. And in that case, we can call method directly again, but this poses the question, how do we know what bar and bus return? And here we can enjoy something that none of dynamic compilers can even dream of. A static compiler can use, within reason, as much time and memory for optimizing your application as it needs. For instance, it can scan all methods of your program prior to optimizations and compute some useful information about each. For instance, it can compute instances of what classes are returned from concrete methods. In starting our analysis from a list methods that do not call anything up to call hierarchy, we can compute such information quite efficiently. And thus, information what methods bar and bus return often becomes available. And the analysis that analyze all methods of your program is called global analysis. What else it can be used for? How about detecting if a method parameter is not escaped into shared memory? This information can be used in escape analysis that determines whether a locally created object escapes from the method stack frame into shared memory. If it appears that it doesn't escape, it can be allocated on a stack rather than a heap. Escape analysis cannot, local escape analysis cannot detect such objects if object is passed as a parameter to other methods. Probably you know that HotSpot does escape an allocation, but optimization. But in order to do that, it should inline all methods where to which subject for stack allocation is passed as a parameter. But it is not always possible to inline such methods. Hopefully, with the help of global analysis, it is not needed to often it is not needed to know about it because we know if a parameter is not escaped into shared memory or not. And I'm going to demonstrate you how it all works together. Let's say we have a pretty frequent coded pattern, iteration over collection. First, JavaC compiler will actually desugar this into a code that's similar to the following code. We get iterator from collection, and with the help of has, next, and next methods, do iteration over a collection. How can we optimize such a frequent code pattern? Please note that has, next, and next methods are abstract, so we know nothing about them in general case. But what if we have some bits of information from global analysis? Let's say global analysis has shown us that get collection always return an array list instance. And things suddenly become much better because we know everything about array list. And for instance, we know what iterator method does in that class. And if we inline it, we see that iterator becomes not an abstract iterator, but a concrete iterator. And we know everything about this iterator. For instance, we know that in its has, next, and next methods, iterator object is not escaped. So we can allocate that object on the stack. And if we inline constructor, we can see its fields. And then we can inline has, next, and next methods. And what we see that iterator object is not used as iterator anymore. It is used as a set of fields. So we can transform into local method variables. And what we see now? We see that it is simple for with a counter. Its inductive variable was an instance field of unknown object before the optimization. And now it can be allocated on a register. The loop can be versioned. All runtime checks can be removed from the fast version. We can inline do something, move all its loop invariants out of the loop. And finally, we will get the most effective code for this quite pretty code pattern. And I would like to emphasize that we did all that amazing tricks based on only on the results of a static analysis, without executing that code any single time. So, concluding my talk about performance, I would like to say that optimizations, analysis, and respective internal representation can be quite sophisticated and require a lot of computational resources. And as you have just seen, it is not enough to perform optimization only once, because some optimization can give opportunity to other optimizations. So ideally, you should repeat them until reaching a fixed point. And global analysis actually depends on the whole program. So a volume information it produces depends on the whole linearly on the whole program. And in our static compiler, for instance, we store results of global analysis on the hard drive because it does not fit into RAM. So finally the question is, can a JIT compiler afford all of that? It shares CPU and memory with your application. And if first 2 points are arguable, I can say for sure that global analysis is not for dynamic compilers. Really, can you imagine that dynamic compiler will use gigabytes of disk space to optimize your application? But what dynamic compilers are good for? First, it can compile not all code of your application, but only those that are actually executed. And it is the main advantage of dynamic compilers, actually. From our experiments we performed several times, profile-guided optimization do not give much performance, but it is enough to compile hundreds less of code to achieve acceptable, than static compilers to achieve acceptable performance. And this observation makes dynamic compilation at all possible. And then the dynamic compiler can devirtualize calls based not on a static analysis, but on actual execution profile. So if it sees that at a certain call site the target method was always the same. It can assume that it will be the same the next time and in the future and inline it. And extrapolating the technique, it can see hot execution traces in your program, row them in basic blocks, and optimize very aggressively. It works and works very well. But I would like to ask you, what happens when an app has no distantly hot code running on a conventional JVM? It often holds, for instance, for UI-centric application, when you have many code for menus, windows, event handlers, and so on. And all that code is executed not frequently enough on a conventional JVM to justify its JIT compilation. So that code is simply interpreted on a conventional JVM. And it, of course, influences user perception of the application. For instance, if we present the same application running on conventional JVM and statically compiled to a user, he will not notice a difference for the first time, but after working on in that application for several times, he will note that statically compiled application responds to its input faster. So static compilation works better for UI-centric application because it compiles every single method of a program, applying the most aggressive optimization as possible. And the difference can be demonstrated on the following slide. Here we compare, it is a chart showing JFCMark benchmark. It is a benchmark that we created several years ago to measure UI responsiveness. It takes a 7set2 demo from JDK and manipulates it with help of robot. Open closes windows, modal dialogues, scrolls down rich text control, and so on. And the benchmark has two modes. Short run is indicative when you just run your UI application, and long run when you use it for several hours, for instance. And here the performance of Excelsior JIT, HotSpot client, HotSpot server are compared. As you can see, in a short run, statically compiled applications runs 2 times faster than HotSpot client. And in the long run, HotSpot becomes faster, but it is still 1.5 slower than statically compiled code. But you may ask, who writes client-side software in Java nowadays? All we have server-side, and on server-side, dynamic approach works better, of course. But I would like to ask you, can a static compiler use dynamic execution profile as input? And the answer is yes, of course. Actually, all modern C compilers implement profile-guided optimizations. But it can be not so convenient to feed static compiler with a profiler for UI-centric application every time you need to rebuild your application. But as you can remember, everything is more or less good for UI-centric application with and without execution profile. But when we move on the server side, we can know that after working on a high load generated by real users, application execution profile will likely stabilize. No new classes will be loaded, and JIT compiler sits idle. And what if we, at that moment, send an actual execution profile to another server, where static compiler installed and won't having relaxed memory time constraints and having an actual execution profile, it can transform your application, it can optimize the application in the most effective way. And this scenario, I believe, is exact scenario where static compilation can be beneficial on the server side. Moreover, Bytecode Excelsior already have some satisfied users on the server side. Some of them benefit that the performance of statically compiled applications is stable, There is no de-optimizations that can occur at unknown time, so latency latency much more predictable. And some of them benefits for better startup time, which is 2-3 times better than for conventional JVM, and it can be important for when you need to run a bunch of microservices simultaneously. And when a statically compiled server started, work as the same as other servers in the cluster, so load balancing does not suffer. Let's now move to another side of the spectrum, to embedded Java. To an outsider, it may appear that if time has stopped in embedded world, processors are years behind those that are used in today's desktop and server computers, and other computational resources such as random access memory are often scarce. Now, the weaker the hardware is, the more expensive dynamic compilation becomes. Resource constraints simply don't let dynamic compilers to work in full force. So for embedded systems, static compiler is just the ticket. Little known fact that some microsystems before and Oracle now always included static compilers in their Java ME offerings. And somewhere between desktop and embedded worlds lays beautiful world of mobile devices. Let's now think how JVM can look on mobile platform. First, it of course needs platform classes, memory manager and GC. Reflection can work without reflection, but I would rather say not. JIT compiler. What's missing? The charger. All that modern mobile devices have a battery. Is it worth to spend battery on every application start that can be reused later? So probably it is it was the reason why Steve Jobs prohibited any dynamic compilation on iOS. It leaves static compilation as the only viable alternative on iOS. What static compilers actually exist? At the turn of century, it was a half of dozen of them, but only 2 have survived. It is Excelsior JET and GCG. But GCG was not evolved several years, and it is finally died this year. And with iOS appearance, we can observe a new Java static compilation boom. All wants to bring Java to iOS, and there are several solutions. Until this year, the most famous was RoboVM, but then it was acquired by Xamarin. Xamarin was acquired by Microsoft that decided to kill RoboVM. But you can use multi-OS engine now. It exists for iOS as well. And you know that Android has ART, that is also static compiler for Java. But all those solutions are used Android class libraries, so they are not Java compatible. And as I said, Oracle always had static compilers for their Java ME offerings. IBM has static compiler for Java SE embedded. And we cover, at Excelsior, we cover desktop servers and embedded. And we are going to move to mobile as well. And we believe that our solution will be Java compatible on mobile platforms. And probably you have heard that ahead of time compiler will finally appear in Java 9 as well, in HotSpot and OpenJDK under the JEP 295. So Oracle always tried to convince that static compilers for Java are not needed, but now it seems they changed their mind. So let's sum up. So today you have learned that static compilation of Java applications is possible while preserving all Java features, and it can be useful. It can be useful for overall user experience, tamper resistance, protecting your application from reverse engineering, better stop time, etc., etc. But anyway, JIT and AOT have their unique advantages. So I believe that synthesis of those two approaches will bring us the maximum benefits in terms of performance. So thank you very much for your attention. Your questions, and I have some T-shirts for questions. Huh? 2 slides back, okay.
Raise up your hand.
Another one?
When Java crashes, it produces stack trace. When code is statically compiled, what it produces?
It produces stack trace, because if we talk about our implementation, which is Java compatible, we have to produce Java stack trace, of course. And it works. Every single Java feature works for statically compiled code, at least for our implementation. And you have a T-shirt. What else?
Which versions of Java do you support, and which target platforms do you support?
We support now Java 8, Windows, Linux, macOS for x86 and AMD 164, and ARM, Linux ARM 32 for our embedded solution.